Hello everyone, welcome back to another video on mathematics, and today we'll be covering one of the most feared topics in the entirety of H2 math, which is vectors. So how we're going to teach vectors is we're going to split it into two videos, and in the first video we're going to explain all the key concepts you'll need to know about vectors, and in the second part of this series we are going to explain the problem solving strategies that you'll be needing to excel in this topic and not be scared of it anymore. Alright, so let's get started. So in the H2 syllabus, there are actually two kinds of problems. So the first kind of problem, which we call type 1, are theoretical vectors problems. So the good and sound knowledge of vector theory, manipulation of vector operations is needed, and usually you don't have any information on the numerical values of the vectors. And for the second kind of problem we call type 2, it will be more of the application of vectors in 3D geometry. And to do this, we need problem-solving strategies, which we will be covering in the second video. But for today, we'll be focusing on the theory behind vectors and what vectors even are in the first place. So look at this kind of question. So this is an example of a type 1 question with just pure theory about vectors and no numbers and no numerical vectors involved. So first, let me introduce to you what vectors are all about. So to do that, we have to bring up the Cartesian coordinate system, which we would all be familiar with in secondary school, and at least the one on the left. So the one on the left is a 2D Cartesian coordinate system, and each point is labeled as the x-coordinate, which is the value on the x-axis, 2, 3, which is the value on the y-coordinate. So in H2 mathematics, vectors is basically in vectors, we are not working in the 2D world, but rather we are working in a 3-dimensional world, which is why we need an additional axis, z. So to do that, we would have to introduce an extra point, x, y, z for our z coordinate. Okay, moving on. So a vector has both magnitude and direction, while a scalar, just like a normal number, a scalar has magnitude but no direction. So what vectors actually are they aren't points, but vectors are instead a set of instructions on directions. So they tell you how to move. They don't tell you where to start or where to end, but they are just telling you which direction to go and by how far. So for example, the instruction drive 20 kilometers towards the north could be an example of a vector. So this is rather meaningless if you don't tell me where to start, because if you're at City Hall, you might end up at Yishun, but if you're at Yishun, you might end up in Malaysia. So a vector alone isn't very useful. So how we write vectors is it is represented by 3 different numbers stacked vertically. So the first number here would be the number of units to travel in the x direction. So this would be 0 over here, which means it doesn't have to move along the x-axis. 1 unit in the positive y direction and 2 units in the positive z direction. Of course, each number inside can be negative. For example, -2 here would mean 2 units in the negative z direction. So as stated earlier, we can't do much with this information alone because it doesn't give us a starting point. But if I tell you to find point A, for example, we want to apply this vector from the origin. And we know that the origin in a 3D space is 0, 0, 0. You can easily do so because you know where to start and you have the instructions on how to travel from that point. So for example, if I give you the vector 2, 3, 5. And we want to start from the origin 0, 0, 0. So let's follow this set of instructions. So first we have to move by 2 units in the positive x direction, causing our new point to have an x coordinate of 2. Likewise, y coordinate of 3 and z coordinate of 5. So we realize that this vector right here actually represents this point we have over here, and these are what we call positional vectors. Positional vectors are vectors that are essentially applied from the origin 0, 0, 0. So of course you can apply vectors from other starting points as well. But the positional vector of a point can be defined as follows. So there are 2 ways in the exams we mainly denote vectors. So the first way is if we are given, let's say, 2 points written in capital letters, and we draw a vector connecting them. So do note that a vector has direction, so we have to add an arrowhead at the end. So we will write this vector over here as AB with an arrow sign on top. Okay, it has to be pointing towards the same direction the vector is pointing to in your diagram. But if you're given a vector without a start and end point, maybe just a letter, usually we use a small letter, we will have to write a curly line below. This applies for all vectors which we use a small letter for. But do note that in the kind of questions they like to set, they like to type vectors as well. And usually when these kind of vectors appear in a question, they don't have a curly line below. Instead, it will be the letter in small caps but bolded. So the difference is this is the handwritten version and this is the typed version. Okay, so moving on. Next, we talk about vector addition. So we can actually add vectors in the following manner. So to add vectors, we basically just combine the numbers like this. Because if you think about it, it's kind of like two separate instructions. This instruction tells you to move 1 unit in the x direction, and this one tells you to move 2 units in the x direction. So if you combine it into one set of instructions, you are ultimately going to be moving 3 units in the x direction because you moved 1 and 2 in a separate sets, right? So generally, we can write it as this format over here. So we are just adding up the pairs of numbers. So how else can we display this? We can illustrate this in a geometric fashion. So consider this vector. And if we want to add another vector to it, the tail end of the second vector must be connected to the head of the first vector. So perhaps this vector plus this vector. So you just follow it kind of like a chain. Call this vector A and call this vector B. So vector A plus vector B is actually equals to two separate instructions combined into one. If we look here, so it's basically taking the start point, taking the end point, and drawing a vector. So we can say that A plus B equals to C. Alright, so moving on, we next talk about vector subtraction. So we think of vector subtraction as vector addition as well, but instead we are adding the negative of the vector. So what is the negative of a vector? So given, let's say, a vector 1, 2, 3, so instead of transversing 1 unit in the positive x direction, we now want to go 1 unit in the negative x direction, which we denoted as -1, -2, and -3. So say this vector looks like this. The negative of the vector would be the exact same line pointing in the same general direction with the arrowhead facing the other side. So suppose we want to add two vectors, suppose we want to subtract two vectors, A and B. We want to find A minus B. What we do is instead we add the negative of vector B, which would be this. And now we find that we are able to add A and minus B because the tail end of minus B is connected to the head of vector A. So our resultant vector A minus B would simply be vector C over here. Okay, so moving on, we can also multiply a vector by a scalar number n. So just a normal number, like you can think of like 5 or -1 or 3. So in order to do that, we basically just multiply n into each component of the vector, as shown here. So what we are doing when we multiply a vector by the number n is actually we are adding it n times. So it may look like this. Say we have a vector, we just want to add many copies to it, so there are n copies of this vector. So the resultant vector will still be pointing in the same general direction. Okay, so scalar multiplication does not change the general direction of a vector. But if n is a negative number, the direction of the arrow will be reversed and the arrow will be pointing here instead. But however, it's still in the same general direction. And we can see that although the general direction does not change, the length of the vector is increased by a magnitude of n because as we stack up the vectors, the length of the resultant vector is many times the length of the original vector. Alright, so moving on to parallel vectors. Two vectors are parallel to each other if one is a scalar multiple of the other. So we know that vectors do not necessarily have to have a starting point. So this vector and this vector are basically the same thing. So consider two parallel lines, not necessarily starting from the same point. Now we can easily move this vector upwards to superimpose with the vector, that we drew here. So something like this. And now that we know Now as we can see that, these two are lying on the same line, this vector in red must be a scalar multiple of the vector in black. So for example, we could have 1, 2, 3, and 3, 6, 9. So the long vector will be equal to 3 times of the small vector. So these two are proven to be parallel to each other. Okay, so collinear points. So what are collinear points? Collinear points is basically given 3 points, say A, B, and C. You are able to draw a straight line that passes through all 3 of these points. So basically, the 3 points all lie on a straight line. So what is the criterion for points to lie on a straight line? So if we take 2 points, let's say A and B, so we draw A and B, and we draw a vector connecting A and B. And now we take another point C, and we want to draw the vector from A to C. We realize that A, B, and C will only lie on a straight line if C is along this line as well, which means that vector AB has to be a scalar multiple of vector AC. So we'll write it like this. Vector AB is parallel to vector AC, or vector AB is a scalar multiple of vector AC. Now you might be wondering, why is this sufficient? Because they share a common point. Because if you have 2 parallel lines that don't share a common point, obviously these 4 points do not have to lie on the same line, right? But if they share a common point and they are also parallel, they have to lie on the same line. So this is just an extension of what we mentioned earlier about parallel vectors. So now let's talk about the magnitude of a vector. So the magnitude of a vector is actually just a fancy way of talking about the length of a vector. So this is also called the modulus, and it's denoted by these 2 signs that look like the modulus sign, absolute value. So let's say we have a vector A. This mod A would be the magnitude of the vector. So how do we calculate the magnitude of a 3D vector? So we know that in the 2D world, we can use Pythagoras theorem to obtain the formula square root x squared plus y squared, something like that. So in the 3D world, we would have to find the length of, say, B to H, where it's moving in the x, y, and z axis. So we can call this, let's say, x, y, and z. And applying Pythagoras theorem on triangle ADB, we get that side length DB is equals to square root x squared plus y squared. Now if we look at triangle DHB, we realize that this is actually a right angle as well, HDB. So if we use Pythagoras theorem on this again, we will be able to get that the length is square root of x squared plus y squared plus z squared. So in general, if we have a vector x1, y1, z1, the magnitude of this vector, which is the length of this vector, would be equals to square root of x1 squared plus y1 squared plus z1 squared. So this is the formula for the magnitude of a vector. Okay, moving on to unit vectors. So unit vectors are basically vectors that give us information on only direction and not magnitude, because all unit vectors have a length or magnitude of 1. So say we have a vector 3, 4, and 5. The magnitude of this vector is square root 3 squared plus 4 squared plus 5 squared equals to 50. And we realize that this magnitude here is not quite 1. So it's a lot bigger than 1. So the unit vector of this vector may be somewhere along the vector or somewhere parallel to it and has a length of 1. So how do we find the unit vector of a given vector, let's say 3, 4, 5? All we have to do is first find the magnitude of the original vector and then proceed to divide each number in the original vector by this number. So our unit vector would be 3 over square root 50, 4 over square root 50, and 5 over square root 50. And a simple check with Pythagoras theorem would show that the magnitude of this vector is actually 1. So this is how we find unit vectors. And another thing to note about unit vectors, let's say the unit vector of A, is usually denoted with an arrowhead-like symbol on top of it. So this will tell you that it's a unit vector and not just any vector. Okay, so there are 3 special unit vectors which we want to talk about, which all have a magnitude of 1. So these are I, j, and k. So if we consider the axes again, so if we draw pairs of x, y, and z axes. The I vector would simply be the unit vector along the x-axis. So I is here, likewise j is here, and k along the z-axis is here. But these are unit vectors, so they only have a length of 1. So these are the special unit vectors that may come out sometimes, which you need to take note of. Alright, so moving on to something more challenging. It's what we call ratio theorem. So given two vectors that coincide at a point, we can form a triangle with these two vectors a and b. So suppose that there is this line here, or this vector, that divides the remaining side into two separate regions. One with length, or just a length ratio will do, lambda and mu. So how do we find this, the vector of this line here, given vector A, vector B, and the ratio of the two sides that it divides it into? So we actually use this rather complicated looking formula over here, but at close glance it isn't actually that complicated. So what we do is we take this scalar over here, mu, and multiply it to the vector opposite of it, so vector A. And we add lambda and multiply across to the vector opposite of it, b, and then we divide it by the sum of these two sides. Okay, so this is how we get the vector in ratio theorem, using ratio theorem. Okay, so do remember that lambda and mu don't have to be the exact lengths, they can just be a ratio. For example, it tells you that r divides the remaining side into a length ratio of 1:3. Then you'll just be doing 3a plus b divided by 4. And this is equals to your vector r. So moving on to what we call linear combination. So honestly, linear combination is just a very chim way of taking, say we have two vectors a and b, and we want to add them together, but before adding them together, we add some coefficients in front of them. So it can just be 3a plus 4b. So let's say our a is 1, 2, and 3, and our b is perhaps 4, 5, and 6. So this would be equals to 19, 26, and 33. So what we can say is 19, 26, 33 can be expressed as a linear combination of this vector and this vector. Okay, so what's the big deal about linear combination? So there's actually this theorem that states that, okay, so if you have this thing here, that's true. So for example, if 3a plus 5b is equals to lambda a plus mu b, and you also know that a and b are not parallel. If you have this equation over here, this will tell you that lambda is equals to 3 and mu is equals to 5. But why is this so? Why can't it be, say, 3a plus 5b equals to 6a plus 3b? So let's say this is possible. Okay, let's move the a and b terms around so we get 2b equals to 3a. And if we divide both sides by 2, we get b equals to 3 over 2a. But this would mean that since b is now a scalar multiple of vector a and b are parallel. But our condition was that a and b are not parallel. So this is the important theorem. Whenever you are basically comparing coefficients, you can just compare. You can just conclude that lambda is equals to 3 and mu is equals to 5 without any hesitation at all. Next, we want to move into some more complicated concepts, dot product and cross product. So we start with dot product first. So dot product is actually equals to this formula over here. A dot b is equals to the magnitude of a multiplied by the magnitude of b multiplied by the cosine of the angle in between these vectors. So what is the significance of dot product? So let's move on and look at some properties of dot product. So I have the formula for dot product written on top here. So the dot product actually obeys the commutative, distributive, and associative laws. So you can use them as follows. You can flip the b and a around. It wouldn't matter. This is an equal sign here. But the one we want to look at is what happens if the angle in between the two vectors is equals to 90, which means theta is equals to 90. Okay, let's say we have a here and b here. What happens if these two vectors are perpendicular to each other? Cosine of 90 is equals to 0, right? And seeing that this part here, this is a magnitude, so it's a scalar, This is also a magnitude, so it's a scalar, and cosine is a scalar as well. So the dot product of two vectors will give you a scalar, so it's sometimes called scalar product. So what I mean by theta being 90 is that A dot B will be equals to 0 only when A and B are perpendicular, because cosine 90 equals to 0. So this is very useful in proving that two vectors are perpendicular. All you have to show is that their dot product is equals to 0. So for example, if we pick the unit vectors just now, I, j, and k, which lie on the 3D axis, any two of them are perpendicular, so their dot products will be equals to 0. And do note that this 0 is really a scalar, it's not a vector or anything, because the result is going to give you a scalar. Okay, and there's another result here which states that if we dot two of the same vector together, we'll get the magnitude squared. This is not as useful for now, but we'll see how it is useful when learning problem-solving strategies, because this is often an important technique in manipulating vectors equations. We often want to use this. So it's not so intuitive, but we will learn it by practicing questions. Okay, so if we see I dot I equals to j dot j equals to k dot k equals to 1, because using this formula over here, the modulus of these unit vectors will be equals to 1, right? So 1 squared equals to 1. And the reason it's equals to this and we don't have the cosine term over here is because two identical vectors would have an angle 0 apart, because they don't even intersect. So cosine 0 equals to 1, so you can just get rid of this part of the formula. So the burning question we must all have now is, how do we calculate this funny thing called dot product? So it turns out that it's actually very simple. So if we have, say, two vectors, 1, 2, 3, and 4, 5, 6, all we do is take each pair of numbers, multiply them together. So we get 4, 10, and 18, and we just add it all up together. So we get 32. So the dot product of these two vectors is simply 32. Next, let's move on to cross product. So cross product has a very similar looking formula, which may look a bit more difficult. But the key here we want to focus on is this part of the cross product. This is the normal. So what is a normal? So let's say I give you the axes again, x, y, and z. Okay, any vector lying along the z-axis, for example, k, j, and I. A normal vector is a vector that is perpendicular to another vector. So the normal here has to be perpendicular to both a and b. So if we cross I and j, the vector that will be perpendicular to both I and j will be k, because this is 90 and this is 90. So our answer will be a scalar multiple of vector k. So remember, crossing two vectors gives us the vector that is perpendicular to both vectors that were crossed. Okay, so here are some properties of cross product, and as usual we have the formula of cross product written above here. So it is distributive and associative as well, but it is not commutative. This is a very frequently made mistake. There's actually a minus sign in front if we want to switch b and a around. Next, because there is a sine theta term inside a cross b, when theta is equals to 0, a cross b will be equals to 0. But it is not quite equals to 0, but it's equals to the 0 vector. Because we see, although this part is a scalar here, we are actually multiplying it by a vector. So we can see that vectors, when crossed together, the resultant answer is a vector. So unlike dot product where we get a scalar, cross product is also sometimes called vector product, because when you cross two vectors together, we get another vector. You can only get a scalar if you take the magnitude of the crossed product, then you get a scalar. Okay, so a cross b will be equals to the 0 vector, but if you take the magnitude of a cross b, we'll get 0. So as explained earlier, using the axis, any two unit vectors crossed together will give you the other one, because the other one would be perpendicular to both of the previous ones. Okay, so how do we calculate this cross product? So there's actually a very complicated formula over here, but it's best demonstrated using an example. So consider 1, 2, 3, and you cross 4, 5, 6. We first start with the number in the middle, and we kind of draw like a crisscross. So we draw something like this. And what we'll do is we will take 2, oh my color disappeared, we'll take 2 multiplied by 6, the top one to the bottom one first, minus the other pair, 3 times 5. And we do the same for the other pairs, next going on to this number, and by right it should pair with a number at the bottom, but there's no more number at the bottom of the vector, so we pair with the top number instead. So it becomes 3 times 4 minus 1 times 6. And last but not least, we have 1 times 5 minus 2 times 4. So after we cross these two vectors, we get minus 3, 6, and minus 3. But don't worry if you cannot remember this formula, because it is very difficult to remember. It is included in the formula sheet MF26 or whichever formula sheet you're given for your A-levels. So not to worry, you can easily reference this if you forget. Okay, so there's one more thing about cross product I would like to mention. So the area of a triangle, as we have all learned in secondary school, is equals to half AB sine the angle in the middle. And do you realize this portion here looks very familiar? This portion here is equals to something like our cross product. When we write our cross product, we get AB sine theta and mod of this. So realize what we're doing is we are just modding the entire thing, so we're adding modular signs to both sides. And the modulus of the unit vector is definitely 1. So this is just equals to this. So the area of a triangle is actually equals to half of the magnitude of A cross B. It can't be without the magnitude, because A cross B will give you a vector, and it doesn't make sense for the area of a triangle to be a vector, right? So we have to find the magnitude for it to become a scalar. Okay, next we want to talk about the equation of a line. So we first start with the most fundamental and the one that's most frequently tested, vector equation. So the vector equation is written as follows. Everything denoted with R just means any point. It just means the set of points that the line can take. So A is a point on the line, and B would be a vector parallel to the line. So let's say we want to find the equation of this line, okay? I tell you that the point 2, 4, 3 lies on it, and it is parallel to the vector 3, 5, 6. Then our equation will be equals to R equals to 2, 4, 3, point on the line, plus lambda multiplied by 3, 5, 6. Now all we have to do to find different points on the line is just sub in different values of lambda, anything you want. Let's say you sub in lambda equals to 1, then your R will be equals to 599. So the point 599 would be a point on the line. So that is it for vector equation, and what we can do is we can write each of these vectors in full, so in their 3-element form as shown here. And after we write this, right, after we write this format over here, we can kind of take out each line. So x equals to a1 plus lambda times b1, y equals to a2 plus lambda times b2, z equals to a3 plus lambda times b3. So it will look something like this. And if we write it in this form, a system of equations as denoted by this curly brace over here, this would be what we call the parametric equation. And if we simplify this even further by equating all the lambda values together, so for example, lambda equals to x minus a1 over b1, lambda equals to y minus a2 over b2, lambda equals to z minus a3 over b3. If we were to equate all of these equal values of lambda together, what we get is the Cartesian equation. But what happens if one of these b values is 0? We can't possibly be dividing by 0, right? So we'll write the other two first, and we look at the last one. Let's go back to this. If b3 is equals to 0, z will simply be equals to a3, because this part of the equation will be 0. So we just write lambda equals to these two equals, and z equals to a3. So this is how we express the Cartesian equation format. Note that usually a1 and b1 are values that you should be filling in yourselves, so they should be actual numbers like 1 and 4, and not something so generic. Okay, so here is a summary for the equation of a line, and feel free to pause here to copy down, or to just jog your memory and make sure you still remember what we just explained. Alright, so moving on next to the equation of a plane. The equation of a plane. Okay, first, what is a plane? A plane is kind of like a piece of paper. Okay, a plane can have many vectors on it, but it's basically just a piece of paper. So the vector equation is very similar to that of a line, just that we have to add an extra clause. So as you might guess, A is a point on the plane. So let's say this is point A. B and C are vectors lying on the surface of the plane. So B and C could be something like this. Or it could also be something like this and this. Okay, and lambda and mu are just real values. You just change the values of lambda and mu in order to get your set of values of R. So let's say you try lambda equals 1, mu equals 2, and you have these three in place already. Then you'll be able to obtain a point that lies on the plane. Okay, so next we want to talk about scalar product form, because we know that with every plane comes a normal. So let's say we have a plane over here. A normal would be a vector that is perpendicular to this plane. And how do we do that? We know that if we cross two vectors, we are able to find the normal, right? So all we have to do is take just now's vector B and vector C, which are lying on the plane, perpendicular to the plane. And all we have to do is cross them together. So B cross C should give us our normal vector. And this is the other alternative form written in scalar product, r dot n equals to a dot n. Here, a is any point on the plane you pick. N is the normal vector, which can be evaluated by finding the cross product of two vectors that lie on the plane. And this set of points R is once again the set of points that forms the entire plane. Okay, last but not least, there's an alternative way to express the equation of a plane, which is via the Cartesian equation. So how we do Cartesian equation is basically the same as how we did Cartesian equation for equation of a line. So what we do is we write R as x, y, z, and n as n1, n2, n3. And we use what we know about dot product to expand it as follows, like so. So n1x plus n2y plus n3z should give you d. So an actual Cartesian equation might look something like 3x plus 4y plus 2z equals to 7. This might be the equation, this might be the Cartesian equation of a plane. Alright, so summing up, here are the possible different equations of a plane, and feel free to pause here if you need to copy it down, or if you need just a brief overview of all of the possible equations of a plane so that you don't get confused. Alright, so we have come to the end of the first part of our vectors course. Do stay tuned for the second video, which will be explaining important problem-solving strategies in solving vectors questions that can come out in the H2 paper. So stay tuned.